So our speaker today is Saad Mouti, who is a new VP in our department. Saad got his PhD in 2017 from Paris 6, and then he spent 3 years at Berkeley at the CEDAR, working with Lisa Goldberg and other folks. And so I think today, Saad, you're going to tell us 2 talks, right? 2 short talks on 2 different topics.
Yes, that's right.
So two half-hour talks. So the first one is on optimal option purchasing strategy with market impact. So it was all yours.
Yes, thank you. Thank you for inviting me. This first talk is kind of from the archive of my PhD thesis. Seeing different topics the team is working on. I thought that it has some closeness, and then a second talk will be more related to what I did during the postdoc, which is interest in ESG investing and factor models. So yeah, the first one, the title is on optimal option purchasing strategy with market impacts. It was an interest to my funding company, which is AXA, who are an insurance company who had a high exposure to options used to hedge their variable annuities books. And so variable annuities are just option-like products that have long maturity, large volume, but also significant market exposure and require hedging. Insurance companies use derivative instruments to manage and mitigate a variety of risk, and variable annuities is one of them. They're actually option-like products. There just has other additional features. So in the US, the insurer's derivative exposure, as measured by the national value just as of year end 2018, is around 2.6 trillion, which increased by 9% from 2017. And life companies reported 96% of the notional value compared to PNC companies, which accounted only for 3.3%. US insurer derivative exposure was mainly focused. They actually use the derivatives for hedging. The number one hedging products are swaps and then vanilla options. And in addition to that, I just read just recently that option volume increased by around 60% just in 2020, with the retail investors kind of investing a lot in options through different new trading platform. So the importance of options and the account for market impact and potentially improving the cost of acquiring large portfolios is of great importance. So it is a common practice for stocks to split large trades to minimize the market impact generated by these trades. This problem was studied in the literature, or kind of pioneered by Green and Chris in 2000, and Gaither and Sheed also followed this framework for log normal underlying process. On the hedging and pricing of option side, Abergel and Lepere, Guillaume and Pou and Lepere also have a number of papers who try to see the option pricing when the underlying asset is subject to market impact. So in this talk, we are interested in defining option execution price that takes into account the size of a trade as a driver of the option price, and then try to find an optimal strategy when the agent has to buy a given quantity of options and is likely to be subject to market impact. So the first thing we want to do is to define a price under market impacts for the Black-Scholes model, set this framework, and use it for the optimal purchasing problem to minimize one of the two criteria, expected cost or mean variance, and then solve this problem and see how extendable this can be to non-Black-Scholes, non-constant volatility model. So we'll start by seeing how we derive the market impacts for the option, and then we'll see the optimal execution and take a look at some results. So the first part is to review the market impact framework, which assumes that a large trader is aiming to buy X0 shares. The number of shares is described by an absolutely continuous trajectory xt. And for this case, the execution price, S tilde, is defined as ST plus a factor that takes into account two impact terms, an instantaneous impact given by eta xt dot, and then another permanent price impacts that is given by, so the first one is eta, and sorry, so it's actually called delta xt minus x0. Corresponds, and the second part corresponds to the accumulated impact by all transactions until time t. Oh, nu and eta, sorry. So our goal is to develop a market impact for options that is in line with the equity case. And our assumptions are the following. The underlying asset is liquid and the option buyer does not see it affected by his trades. The option trader fixes a strike K and maturity T hat at the beginning of the strategy and only trades this option along the way. And we, for simplicity, we ignore the drift and interest rates. So in the absence of market impacts, the option price is given by the Black-Scholes formula. Yeah, so we use the Lalonde framework for hedging derivatives under proportional transaction costs. That is based on an approximative replication of the European type options for a terminal payoff V capital T under the Black-Scholes framework. This framework leads to a Black-Scholes formula with a suitably enlarged volatility that takes into account the proportional transaction costs. So we consider an option issued at time 0 with maturity T hat. The underlying asset is then given by the under the marginal gain measure given by the stochastic differential equation DST equals sigma ST dWT, where WT is a Brownian motion. The cash flow evolves with 0 risk-free rate. And then the hedging is performed over a discrete grid with n revision dates, T0 until Tn. And we consider that it involves the proportional impact rate is given by I0 and is seen on the underlying asset. So the replication of the option is given by this formula. So the additional term is the sum of the I0 STI of the change in the delta exposure between two revision dates. So Ti is I over N. So we consider that the grids are equally equidistant. And that the strategy delta is on an interval ti minus 1 ti. And that delta in is fti minus 1 measurable. So delta n corresponds to the trading strategy, which is simply the number of shares of the risky asset that the holder who's hedging his option possesses in the period I. So in this case, the option price is a solution to the following PDE. So instead of having the usual sigma squared, here we have a sigma tilde. And this sigma tilde is given by sigma squared plus the additional term that takes into account the transaction costs. Of course, with the final condition of the option payoff. So there are actually some limitations to the loans framework, and mainly when n goes to infinity. But in our case, we fix a n that is of a reasonable order in order to just derive an option price and then work with this. So what corresponds to the proportional transaction cost for the case, for our case, is the term mu xt dot plus eta xt minus x0. So instead of fixing the number of revisions, we fix the revision step defined by h equals t hat minus t over n. And this is regardless of the time to maturity. So our formula for the enlarged volatility becomes becomes sigma squared plus this term that consider the speed of the execution and the quantity left to execute. And this is proportional to the square root of the time to maturity, sigma. Eta tilde and nu tilde are given by this formula, which brings back to the impact, the instantaneous and continuous impact on the asset price. So for the Black-Scholes framework, the option price, once we plug in the new enlarged volatility, can be given by the option price without impact, plus this additional term that is proportional to the power of 3/2 of the time to maturity, that is also proportional to the gamma of the option, and of course to the impact term. So the impact term in this formulation includes the temporary impact and the permanent impact. And xt is the quantity held at time t. Xt dot is the speed of trading in number of options per time unit. So the gamma being positive, the option price with the market impact is actually is higher than the option price without impact. So once we define this this setting and this option execution price under the market impacts constraints, we tackle the optimal execution problem. So for the optimal execution problem, we aim to buy X put options over a finite time horizon. We chose put options because these are the main options insurers buy once they are exposed to variable annuities. And so the the manager wants to buy X options on a given time horizon, 0 to capital T. X defined by xt for t between 0 and capital T is the execution strategy, where x0 is capital X. So strictly lower than 0, just it's common practice as a liquidating a short position. And the aim is for X capital T is to be 0. So as before, we assume that xt is continuous and adapted, and that the option price is given by the formula that we saw earlier. The cost function for the strategy X is the integral between 0 and capital T of pt tilde xt dot dt, which we can, oh, sorry, I have a question on the, how is the gamma? The gamma is the second derivative, of the option in the Black-Scholes framework. So basically, it's actually the vega, but because of the relationship between the two in the Black-Scholes framework, we end up with the gamma.
So it's not on the p tilde. So it's not a nonlinear problem.
So it's not. I'm sorry.
It's not a nonlinear problem. You define the gamma on the p, not on the p tilde.
Yes.
Can you go back to the equation defining?
Yes.
I'm sorry to interrupt.
No.
So if you look at this equation here.
Yes, this one. Mm-hmm.
So when you will replace your sigma tilde, you may end up with a nonlinear problem, no? Because gamma is on p tilde, is not on p.
Yes, it's on p tilde. It's on p tilde, but so p tilde would actually be an option price with sigma tilde.
Yeah.
And then doing an approximation. So this is actually an approximation. Yes, right.
Ah, there is an approximation. Okay.
Yes. Yeah.
Oh, you linearize that part.
Yes, exactly. Yes.
Okay. Okay.
Yeah.
That's what I wanted to know. Thank you.
Yeah. No, thank you. Yeah, I skipped some steps, bro. Thank you. Yes. Yeah. So ideally, yeah, the sigma tilde would actually be inside the PT, but yeah, we linearize it to simplify the problem. And so yeah, I think I actually did a comparison between the prices of the two, and it seemed that the approximation is not that kind of shocking. So the cost of the strategy given by the integral of p tilde xt dot dt can be simplified as minus x p0 minus the integral. So the delta hedging strategy between 0 and capital T plus the impact term. So when we take the expectation of the costs, this term disappears as WT is a martingale, and we're only left with this term and like a constant term. So ultimately, we are interested in minimizing the expectation of this term. So for the case of minimizing the expected value, so minimizing this quantity, also given the fact that this term as well is a martingale in this framework, we have an deterministic solution that is just increasing and convex in T, given by this speed of trading and by this quantity to be held at each time T. So for the case of the variance of the cost, then we need to take a look at the variance. And so the variance is expressed as the expectation of the integral between 0 and capital T xt squared sigma squared st squared and the second derivative of the p tilde plus some terms that arise from the uncertainty in the drift parts. So here we can actually reasonably approximate the second part by only the term in the expectation here. And we aim at minimizing the expectation of this expression here. So we do that in a dynamic programming framework where we define x round tx, the set of all adapted and absolutely continuous strategies, satisfying the given boundary conditions, the integrability conditions on this expectation and this one. And we consider the minimization problem of minimizing over the set of all adapted and absolutely continuous strategies, the integral of this guy here. So this is actually known as a finite fuel problem, where we define a control alpha, where the alpha is minus the speed of trading, and introduce a new set A around Tx, the class of all progressively measurable processes for which the parameterized strategy is defined by this form. And that belongs obviously to the initial one. So among the optimal controls, we are interested in Markovian processes that only depend on the state at time t. And we try to actually find what is the control and what is the value function. So for a given strategy, U is defined by this new form, where all x dot is replaced by the control alpha, and xt is the expectation conditional on the states at time t, so meaning st and xt alpha. The result is that U has to satisfy a singular terminal condition that kind of penalizes an individual who did not liquidate the whole strategy at time capital T by an infinite penalization, and equals 0 when the final state on X is 0. So, of course, in practice, we would substitute the infinite penalty problem with a finite terminal condition. And we consider a parameterized value function by the parameter epsilon, where U epsilon at the final state is 1 over epsilon sigma x, which would be 0 if x equals 0, and large enough to penalize any strategy that does not leads to a 0 number of options to liquidate at maturity. And the value function is given by the expectation of this guy here at each time t. So this is a solution to to a partial differential equation that is quadratic in the partial derivative of u epsilon to x, and that has other dependencies on the delta, and that has the usual heat equation term. So U star epsilon is the unique solution to the optimal execution problem, and alpha star, which is the control, is given by this guy here, which depends on the derivative, the partial derivative of u to x, and is inversely proportional to the gamma and to s squared, and to the term that we actually initially saw in the expectation term, which is the power of t hat minus t to the 3/2. To actually derive the AGB, the Hamilton-Jacobi-Bellman equation, we reparameterize our problem to a new control variable kappa that is multiplicative to xt. In that case, we can simplify the value function u to x squared times a lowercase u. And then we try to actually solve the problem with the lowercase. Yeah, the new parameterization just defines the quantity held at time t as x times exponential minus the integral between 0 and t kappa s ds, and for any time u, it's again just a function of the value prior to that at time t times again the integral between t and u of this new control parameter kappa. The reduced problem is given by this guy here, and then by means of Ito's formula, we can derive the HGB equation where we minimize this guy here. This minimum is achieved at kappa star equals u over t minus u to the 3/2 times s squared gamma of ts. And then we solve this problem, which transforms into the final PDE equation, which is quadratic in u, and has the same kind of previous terms as the previous problem, except from the integral, the partial derivative to x of u squared. And again, we have the final parameters or final condition, which is a penalization by setting a1 over epsilon large enough to constrain the manager to liquidate the position between the time horizon. Okay, again, the expression of kappa star. So, of course, in addition to the PDE, in order to solve it, so we'll solve it using finite difference methods, and for that we define localization and boundary conditions based on heuristics for when S tends to 0, and when S goes to S max, that is greater than the strike K. And so in these two cases, we find variational equations given by this expression, and in the second case by this guy here. So solving this, we use finite differences method, where we linearize the u squared. Although I'm kind of exploring any alternatives that could solve these problems without the additional assumptions and simplifications. And for this case, we consider a parameter of sigma t hat mu r as 0k. What type of action here we actually buy, so which means x0 is -1, eta hat, and the trade-in frequency, and the lambda for the mean variance constraint. So the parameter eta is considered to be kind of in alliance with the stock trading instantaneous impact. And so we want to buy options over a 1-month horizon, and those options are of maturity 1 year. So here we plot the trade-in rate kappa as a function of the asset price and time. And so for lambda equals 0, which corresponds to the Black-Scholes case, and for lambda equals 100, which corresponds to the mean variance. So we can actually find that for lambda equals 0, that it's kind of constant for given at a given time for different values of S, probably except maybe due to numerical reasons on the boundaries. And however, for the mean variance, we see that the trade-in rate increases for low asset prices, and compared to prices around the the strike of the option, and yeah. So if we want to look at the evolution of the trade-in strategy for different simulations of the asset price. So the trade-in rate is again like a convex increasing function, as described from here. The position, however, it's like it actually seems to be linear, but the trading quantity, so between two time periods, is as well an increasing and convex. And we see maybe actually just a little bit that for stock prices that go lower, the trader will tend to start trading actually more when the price goes down, and a little bit less when the price actually goes up. And so, yeah, no, I was actually talking about the case lambda equals 0. So it's kind of in accordance to the numerical case that we actually found, maybe to the except of some numerical reason around some prices. So for the case where lambda equals 100, here the trade-in quantity will tend to actually be higher at the beginning of the strategy. And eventually when time starts to get closer and closer to the maturity, then the trader will urge to end the liquidation. So the position XT is compact. And yeah, and this is actually the main findings for the mean variance case. So I will speak briefly about the extension to local volatility. So in this case, S depends on the underlying stock. In that case, we have actually a PDE that we can actually no longer express in a closed form. So I forgot to mention, so this extension was done by the PNet and Coke in 2014. And so the goal is to actually work with the PDE for the option price and a PDE for the execution strategy. So the execution strategy will have this term, in which case we need to find the value of the option for each value of the control, and then solve the HGV for that given option price for that given value of the control. And then to actually do that, we opted for semi-Lagrangian methods, where the numerical scheme is, so we solve the PDE of the option valuation on each node, as well as calculate the deltas and any partial derivatives with respect to the asset price. Then we actually need to find the an approximate value of the control alpha at each mesh node, give the value of the option and the value of the delta at each node, and then solve with finite differences this equality. So any values that are not in the mesh are obtained by linear interpolation between the values next to it. So in order to move to the other talk, but also as you know, interest in future perspectives, is the you know, an exploration of the nature of market impact for options, especially with the fact that there are both covered and naked options in the market. So our assumption is that the option price market impact is mainly driven by the underlying stocks. And so given also the limitations of finite differences and their instability, would want to explore deep neural networks algorithms to solve the quadratic stochastic control problems and generalize the case of the options PDE, not necessarily just the volatility that depends on the underlying asset, the local volatility model. And this is it for this presentation. Do you want me to move to the other one and then come back for questions? So
Saad, so you have about 15 minutes left, and I don't know. I have some questions on this one, so I'm not sure what would you like to do.
I can actually just roughly speak about the other one in maybe 10 minutes and then have 5 minutes questions. Would that be okay? Or
okay, yeah, let's do that.
Okay. So the other one is I think I actually can go over it quite. So I'll stop this one and then share. So yes, so the other work is actually of interest for studying. So it's an empirical analysis of the cross section of maximum drawdown, with the kind of interest in environmental, social, and governance investing. So what we try to answer is the cross-section variation of maximum drawdown predictable. So can we, based on some set of characteristics, define which stocks are likely to have higher maximum drawdown in the future, and which are less likely to have. We also wanted to, kind of explore the machine learning span and see which models do better in these types of problems. But our first interest was actually to test if in environmental, social, and governance scores. So there are actually nowadays a lot of companies who provide those scores based on what the company discloses, or actually what is said on the media about the company. So for the methodology, we simply regress maximum drawdown to firm characteristics using a pooled regression and 9 machine learning methods. And we look at the predictive power of the firm characteristics through out-of-sample analysis. So we find that from the out-of-sample performance that there's some evidence to the predictability of maximum drawdown, and that a handful of characteristics can and do explain the cross-section, but that ESG variables only marginally improve the prediction. So I'll skip some of the motivations and literature and just show. So basically we have 111 firm characteristics that go from the Fama-French factors like book to market, earnings to price, operational cost, momentum, and also others like option-based ones like the SMERC or short interest, or the difference between implied volatility and realized volatility. Yeah, so we take actually this bunch of characteristics, we plug them. So this is just how many the universe of stocks we used is the Russell 3000 from 1965 to 2019. And so we took these characteristics, we took the maximum drawdown as our predicted variable. And we considered a regression, a pooled regression model where we try to explain forward-looking maximum drawdown as a prediction of current characteristics, where the firm characteristics are cross-sectionally normalized, and we are interested in exploring linear models like ridge, lasso, elastic net, and other nonlinear models like random forests, gradient boosting, or neural networks. So yes, we Winsterize values that are beyond 3 standard deviations. We normalize the factors, and we are mainly interested in the ranking of the predicted maximum drawdown compared to the realized maximum drawdown. So we explore, we kind of give the performance analysis using the Kendall correlation. So yes, so the overall performance of the models gives a slight outperformance to neural networks and gradient boosting trees. We find that large companies has lower performance than small companies, which might somehow also actually hints on what characteristics or are more likely to drive the maximum drawdown. And when we look at the evolution of the correlation over time, the cross-sectional correlation over time, we of course find that overall the the performance is around 50%, except for the period of the 2008 crisis, where most of the models kind of missed the ranking of maximum drawdown. So we can see that through the distribution of the realized maximum drawdown from separating the predicted maximum drawdown into 5 quintiles. So on the right side is the 2008 period, and on the right side is the like a relatively calm period. So we can actually somehow see that that miss performance. So the kind of good news is that using quintile based portfolios, low maximum drawdown stocks outperform high maximum drawdown stocks. And if you actually look at closely at these graphs, you can see that the blue is a low volatility portfolio compared to the purple and red. So what does this actually kind of lead to when we do a feature importance through a permutation feature importance that relies on the change in performance when shuffling the values of a variable? Is that the volatility and realized volatility and idiosyncratic volatility beta are the 3 main drivers. And so it kind of explains that that part where low maximum drawdown stocks are actually low volatility stocks. So in exploring ESG, so what else? Yeah, we can actually also, of course, these are the top 30, we can, or top 20. We can see, of course, size or momentum as one of the, variables, but they are actually barely significant compared to volatilities and beta. So to extend the analysis to ESG variables, we include variables that we collected from 2 data providers. One of them is Owl Analytics. So they aggregate scores from different providers using some KPIs of their own. They set environmental scores, social scores, and governance scores. And they also actually aggregated them. So now kind of managers ask about just one score that allows them to outperform the market, but there are actually problems to doing that eventually. So in that case, we just took the top 30 characteristics that came from the previous analysis, but on a validation set. We then augmented these by the ESG variables, and we rerun our algorithms and took a look at the Kendall correlation for different models and different cases. So the Bayes means just the 30 firm characteristics. Bayes plus OWL, E, S, and G, it means that the 30 plus the environmental and the social and the governance score, and plus ESG is just the final score, TVL or the TVL scores. So True Value Labs is another data provider who uses media to kind of give a scoring to companies based on kind of controversies or good news so they assess actually the positivity or negativity of news, and they map them to the standard, the SASB standard sustainability standard something. Sorry, I forgot. So it's actually just a set of rules of what to look at for a given industry in terms of controversies or good news. So for example, if you are an energy company, then any news about pollution would actually hurt you. Any good news about recycling would actually improve, and that's what they kind of actually use from the media on that. So yes, we actually find that ESG data only marginally improves the performance, and in fact, this improvement is relative to the base model. Although it's positive, it's not actually important enough to assess that they in fact improve the value. If we look at the correlation between ESG scores and maximum drawdown, they're negative, so meaning that high scores tend to have lower maximum drawdown, but this analysis kind of shows that although it might be the case, there are other characteristics that would explain both the maximum drawdown and that the ESG scores are kind of somehow spanned to it. So which actually leads to another analysis which tries to kind of apply some controlling over some characteristics and take ESG scores that are kind of perpendicular to the other characteristics. So in terms of evolution, so the base model on the left, the base plus ESG data on the right. So from the look at these graphs, both are quite actually identical. And in fact, we see that adding the ESG scores does not change the quintiles composition, and that the change in either returns, maximum drawdown, Sharpe ratio, or Kalman ratio is really marginal. So when we look at the top variables, ESG scores are not actually within the very top or 20 top that we kind of have. We still have the volatilities. We have some operating cash flows or firm sensitivity. So yeah, this is then it for the other analysis, which I was supposed to have a bit of more time to go over. But please, if you have any questions or want to discuss, I'd be happy to